Hi guys, I'm here before you to take up the chemical properties of haloalkane. CX bond is very polar. Since CX bond is polar, C has sp3 hybridization in haloalkane and X has got high polarity, right? So CX can be easily broken. If CX can be easily broken, we will have different type of reactions. The flowchart is right in front of you. Substitution, elimination, and we have formation of Grignard under specific conditions. So let's move over to the screen for all the explanation to these reactions. Nucleophilic substitution reactions, we will just see. As we were doing the polarity of the RX bond, we know this is a covalent bond. This is a covalent bond. X gets partial negative charge, R gets partial positive charge. So if we have any reagent, take any reagent. If you take something like NaOH, which will have a positive part to it and a negative part to it. So this will act as a nucleophile. So whichever will be the nucleophilic part, that will be, halogen will be displaced by that, and what you will get is ROH and NaX. So exactly this we have to do. We just have to identify the nucleophilic and electrophilic part from the reagent, and always remember that H plus is always the electrophilic part. Let's move on to the reactions. Guys, this is the entire table where what I have done is I have taken alkyl halide and I have tried to mark the nucleophilic part in red color. So if you can see, this is the nucleophilic part, nucleophilic part, nucleophilic part, nucleophilic part, right? And this all I have taken from reagents. This is sodium hydroxide, second number 2 is water, number 3 is sodium alkoxide, number 4 is sodium iodide, number 5 we are reacting with ammonia, 6 we are reacting with, this is nothing but R, 6th we are reacting with amines, 7th we are reacting with secondary amines, 8th we are reacting with cyanides, 9th also it is cyanide, right? And 11th and 12th the nucleophilic part is NO2, 13th it is silver acetate. So Ag is the plus part and NO8, this part will be alkanoate and this is the negative part. In 14th, H is the nucleophilic part, so we will have electrophilic part as LiAl H4. So here H is acting as a negative, as a nucleophilic part. In again 15th we have, if we have metals which are reacting with alkyl group, so we will have metal as positive, R as negative, and in the 16th we have sodium acetylide, sodium will be the positive part and acetylide is going to be the negative part. What I'll do is, this nucleophilic part, this will displace this nucleophilic part, right? So let's write the product. It is going to be ROH plus NaX. So we get alcohols. In second, again we get alcohols. First and second both we get alcohols. Third we get ethers. Right? So only negative part is displacing the negative part. Fourth it is alkyl halide. Fifth it is amines. Sixth we get secondary amine. Seventh we get tertiary amines. 8th RCN plus KX. Let me tell you, Cn minus is an amident nucleophile. That is, it can get attached via C also or N also. But in this question, it will get attached via C, giving you nitrile because CC bond enthalpy is greater than Cn bond enthalpy, right? Now in the second one, what happens? The structure of AgCN is, it is covalent. Here the bond is, it is attached. So the lone pair on nitrogen, they are available and they make the reaction. So what you get is RNC plus AgX. Again in case of AgONO2, this is silver nitride. Again the attachment is covalent. So the lone pair of nitrogen as well as the lone pair of oxygen in AgNO2 both are available. But nitrogen being less electronegative, what you get is the attachment takes place from N. So what you get is RNO2 plus AgX. In the second one, we get an ambident nucleophile. This ambident nucleophile, this negative charge keeps on rotating on both the oxygen. So the attachment will take place from oxygen, because there is a negative charge on oxygen and charge gives instability. Dissipate the charge, it gets attached via oxygen. So what you get is alkyl nitrite, right? And you get KX. In silver acetate, you get esters. LiAlH4 is a very important compound. In LiAlH4, H is in form of nucleophile hydride. So what you get is RH, nucleophilic substitution, and rest products are LiCl plus AlCl3. If you have a metal which is attached to R, you can get higher alkanes also. Metal gets attached to the X. Now if you have sodium acetylide, beta इसमें भी कार्बन के ऊपर नेगेटिव चार्ज है और सोडियम के ऊपर पॉजिटिव चार्ज है, तो पॉजिटिव चार्ज किससे जाएगा? पॉजिटिव चार्ज विल गो टू X and negative charge will get attached to R, giving you higher alkynes. If you look at the reactions, you are getting all functional groups. Let's do elimination, also known as beta elimination. This is also known as dehydrohalogenation. Why? Because we remove halogen and we remove hydrogen also. And why beta elimination? So in presence of alcoholic KOH, which generates OH minus alcoholic, which is a base, not a nucleophile, a base which makes it undergo elimination. So what happens is this Cl is lost as KCl, right? And this OH will combine with one of the beta H. Now here both the betas are same. This is beta 1 and beta 2 are same. So you get water, and whatever carbocation you get a double bond. So this bond gone and this also one hydrogen gone. So you will have CH3, CH double bond, CH2, you get alkenes. So if you can see, with alcoholic KOH, you get alkene. With aqueous KOH or NaOH, you get alcohols. Come to the second elimination reaction. This is again, I have taken unsymmetrical halide, that is, I have taken somewhere where halogen is attached. This is a different alkyl group and this is a different alkyl group, right? So in this case, what we use is, we use Setzeff rule. Setzeff rule says we have to get more alkylated alkenes. So this definitely this Cl will go, but beta hydrogen, either beta 1 can go or beta 2 can go. So let me write both. So byproducts are minus KCl minus water. If beta 1 goes, then the product is going to be CH3, CH, double bond, CH, CH3. If beta 2 goes, it is CH2, CH, CH2, CH3, right? So this is major product, which is butene, and butene will be the minor product. Now why? Because in this we have only around the double bond, guys please understand, around the double bond there are only 2 hydrogen, so 2 hyperconjugative structures, whereas here around the double bond there are 3 and 3, 6 hydrogen, more hyperconjugative structures, more resonance. So we follow Setzeff rule whenever we have to do beta elimination of a halide where the environment around the carbon to which halogen is attached are different. Let's move on to the last type of reactions, that is reactions with metal. We have 2 different reactions here. One is we treated with magnesium, a reactive metal in dry ether. These are also known as, the product what we get is RMgX, and here there is a bond of carbon with magnesium, so these are known as organometallic compounds. Simple addition reaction. And then there is one more reaction, Wirtz reaction. Here what happens is, when you treat RX with Na in presence of dry ether, now let me write it this way. We have one NaX going like this, then there is one more NaX going like this. We take 2 Na and we get RR, that is alkanes, plus 2 NaX. So this is Wirtz reaction where there is a carbon-carbon bond created, a new. Here there is a carbon and metal bond created. That's all for the chemical properties of haloalkane. That was all about chemical properties of haloalkane, and let me tell you that the mechanism of SN1, SN2 and a comparison will be taken up in the next video. Also the stereochemical aspect of SN1 and SN2 will be taken in the next class. That's all for today's class.